All right, so today we're really starting to get into some fun stuff. It's called the average rate of change. Sounds boring, but you can do a lot of stuff with the average rate of change. This is the basic building blocks of calculus. So here's the formal definition of average rate of change. Functions, which we've been studying left and right. Our rules, in other words, they're just equations. And from these equations, we get outputs when we put inputs in. Sometimes we want to know how fast the outputs are changing compared to the inputs, and that is called the average rate of change. You guys do average rate of change all the time. Nobody's ever called it that. Your walking pace. Sometimes you walk really slow from class to class because you don't want to go to math on time. Or as soon as the bell rings for fifth period is done, you guys bolt out the door to get to lunch. You want to be first in that lunch line, so your speed is faster. You are covering the distance to the cafeteria a lot faster in time than you would walking from, say, English to math. Now, I have got a little thing here, a roller coaster. All right, a roller coaster, whoops, where'd it go? A roller coaster is an average rate of change. Right? So if I do this roller coaster right here, look at it. There it goes. It's slow, it's fast, and then it does a loop-de-loop. So right at the beginning, it's picking up speed, then it slows and goes faster. And there's a whole bunch of rate of changes that are different there. And what's kind of cool about this, if you notice the little website address, you can go and play with this. We can add hills and loops, and we can increase the speed and make the coaster go faster, but let's see if the coaster makes it through this. Oh, oops, kind of fell off the track because we were going too fast to begin with. So let's slow it down. Oh, man, got to go slower. There we go. Do we have enough speed? Oh, we didn't have enough speed to get up the track. So it's a little game that you can play with, and you can design your own roller coaster. Almost. Let's try one more. Let's see. We go up, up, up. Oh, almost. Let's decrease them. But yeah, anyway, you get the idea. You can come and play with this. It's kind of cool. See, you can add as many hills and loops as you want. See if you can get your roller coaster to go. But we're going to be going back to roller coasters later on. But they are a classic average rate of change. So let's start with some basics. We're going to start with rate of change being what you understand the most. Running versus walking. Obviously, running is faster than walking. So in this example 1, we've got Max and his younger sister Evie, and they're going to have a race in the backyard. But Max, being the good older brother, gives his sister a head start, and he tells her they're going to run for 20 seconds. The distance they are along in the race in feet is given here. So in other words, here is Max, M for Max. Here is Evie. And then this is their race. Let's look at the graph. On the bottom is time. Because time is an independent variable, we can't control time, so therefore it is always the independent variable. But how far we are along in the race, the distance, depends on how many seconds have gone by. So let's just make sure we really understand how to read this graph before we start doing any math behind it. So the first question, do we really understand what m of 12 equals 30? Well, the first thing we have to realize that the m stands for max. So we are looking at max right here. And then, do we really understand that this is the x value? And in this case, the x value represents seconds. So this represents 12 seconds. So basically, it's asking, where is max at 12 seconds? Well, I'm going to take a line so I can see it, and I'm going to realize this goes 2, 4, 6, 8, 10, 12. So here's 12 seconds right here. And I want to see at 12 seconds, where does it cross Max's line? Oh, at 30 feet. So Max at 12 seconds is 30 feet into the race. He's not 30 feet above ground. He's just covered 30 feet. All right, next question. If both runners start at T0, what does T0 mean? Oh, they're both starting right at the beginning. No seconds have passed. How much of a head start does Max give his little sister? So they want me to go where the time is 0. Okay, well here it is where time is 0. Max is right here at 0 seconds. And his little sister Evie is right here at 0 seconds. So how far is Evie ahead of Max? Well, this is the distance, and if I count 5, 10, 15, 20, 25, it looks like Max gave his sister a 25-foot head start. Nice older brother. My brother wouldn't have done that for me. Now, does Max ever catch up to his sister? Well, here's Max running. And here's his sister running. And do the blue and the red line ever cross each other? Not that we can tell, because remember, they only ran for 20 seconds. At 20 seconds, Max is still behind his little sister. At no point did he catch up to his sister. Aw, he was the good brother. He let her win and let her feel good. So average rate of change is what we're going to look at now. And it is fancy for something you may have learned last year, slope. It's how the change in y over the change in x. And yes, you may be looking at me going, Mrs. Trulin, you're drawing a triangle. Why are you saying the change? Because this is Greek for a letter called delta. Like Delta Airlines. See, delta is changing your position by flying you. So Greek for delta, and it means to change. So we want to find how far the y's change. In other words, what we do is we take the output and subtract them based on the inputs subtracted. All right, so I'd make sure I wrote that down. Sounds like a good question for a quiz tomorrow. All right, so example 2. We have a function and its equation is x squared plus 3. So in other words, when I input an x, we get its output by squaring the x and adding 3. So for example, if I picked 1, the answer is 4 because 1 squared plus 3 does get me 4. And when I square things, it makes them curve. And then I add 3, so I move up 3. We're going to learn that later on, but just to, not today, that's in chapter 4. But just so you understand that these charts are not made up, that they're actually based on this equation right here. Find the average rate of change from -1 to 3. Okay, so now I'm going to come back here and remember, to find the average rate of change, it's the outputs subtracted over the inputs subtracted. So the first thing I'm going to do is I'm going to take this -1. I know -1 is an input. When I input -1, they say my output is 4. When I input a 3, they say my output is 12. So I want to find the average rate of change. So it tells me to subtract the outputs. Okay, I'm going to subtract them. I'm going to do 12 minus 4. And then on the bottom, they want me to subtract the inputs, but I have to go in the same order. So if I picked 12 first, I have to pick its corresponding input, which is 3 first. And careful, 3 minus a -1. So this is 8 over 4, which is 2. So the average rate of change are 2 y values for every 1 x value. Now you may be asking, but Mrs. Trulin, I didn't want to do it that way. I wanted to do it a different way. I'm going to make that a little smaller so you can still see it, and I'm going to change my pen color so you can see it. What if I decided to use the points backwards? In other words, here I did 12 minus 4. What if somebody decided to do 4 minus 12? And then -1 minus 3. Well, 4 minus 12 is -8. -1 minus 3 is -4. Look, I get the same answer. Because all we're doing is counting how far we changed along the y versus how long we changed along the x. So here we have a function, and it's function h, and it's given in the table below. But we don't have a picture of the function. We just know that it's doing something. We could graph it and get a picture, but no need. Which of the following gives its average rate of change over the interval from 2 to 6? Now, I say which of the following, but I just want you to be able to do the rate of change. So rate of change means how far I changed along the y divided by how far I changed along the x. Well, my x values here, I start at 2 and I go all the way to 6. So now from this chart over here, I can get my corresponding y values. 2 is 9 and 6 is 3. All right, so my y's, I'm going to go from, doesn't matter which way I'm going to go, I'm going to go this way. What did 9 to 3? So 9 minus 3, and so I'm going to follow the same way. 2 minus 6, 9 minus 3 is 6, 2 minus 6 is -4. So my rate of change is -3 over 2. So now if I really were to graph this, hopefully you can understand what this rate of change means. So I'm going to come over here, I'm going to pull out a graph. And if I were to graph these points, there's 0, 10, there's 2, 9, there's 4, 6, and here is 6, 1, 2, 3. Notice what's happening to my graph. It's going down as I plot these points. And if we remember, our rate of change we figured out to be -3 over 2. So do you see what the negative signifies? The negative signifies that we're going down. And they wanted me to start at 2 and end at 6. So if I did my change in y, and I counted it, 1, 2, 3, 4, 5, 6. And then I went over 1, 2, 3, 4. There, and that was that same number we got before. That our y's changed by a value of 6 and our x's changed by a value of 4, and the negative signified that we were going down. Rate of change is how far we change along the y in terms of the x. And it's going to be very important. And we are going to do a lot of rate of change over the rest of the year. Okay, bye.